So this one we're going to talk about signals and switches. Okay. So signals, so going back to what we talked about on Tuesday, what's the difference between digital and analog? Let's kind of go back to that for a minute. What are the differences between digital and analog circuits?
Digital has a variety of signals. And then, I mean, digital is either yes or no, like on and off. And analog has a variety of signals.
Very good. They're two different things, right? You can think of it as, for digital, you have the light switch. It's either your lights are either on or they're off. If you use an analog light switch, that means you've got a dimmer to it. So you don't have as intensive light when you turn it on and off. Does that make sense?
Yes, ma'am.
Okay. So in figure 2-1, you see a timing diagram. And one of the things you see, or should see, is the logic state and something to tell you what the voltage is versus how long the time is. Let's see if I can find that. Okay, so I know most of you don't have your book yet. That's fine. You need to work on getting it though, guys. Because what you should see, turn my camera real quick. If you have your book, you're going to be looking at this guy right here. And you should see, I know it's a terrible video right here, but you should see that timing diagram. And what you should see is how whenever it hits 5 volts, it's a signal for a 1. If it's 0 volts, it has a 0 signal. And that's how they're creating a timing diagram and showing you how the logic state runs. And they're using oscilloscopes to view this. So here's it in a better picture of it. So if you have 5 volts, you're hitting a 1. If you have 0 volts, you hit a 0. This is the premise of digital. There is no in between, right? When it comes to waveform timing, you're looking for something that's repetitive, has a specific time interval. The pulses it gives out need to be identical so that it doesn't confuse itself. The frequency and the time period it takes for it to do all this are crucially important to know what you're doing and how to deal with that particular circuit. Questions so far, guys? Okay. So duty cycle. So how many of you remember the word duty cycle from when you were in AC? I think some of y'all took it. So when you learned about duty cycles, you should have seen the arcs, right? How many times does it go high? Or how long does it go high? Better question on that. And that's the big thing with that one, is that you have to know sometimes exactly what that duty cycle is to be able to become more accurate. Okay. So this one should seem real familiar. You've only been using it since you were in intro. And that is scientific and engineering notation. The one we use is engineering notation. So you have kilo, mega, giga, milli, micro, nano, pico. There's only one that's left out, really, and that's what? What's the fourth big one we talk about? Okay, so the last one's missing is tera. Okay. Last one missing is tera. So you have giga, mega, kilo, milli, micro, nano, pico. This is in your book. Again, the one they forgot about was tera, which is the one that's above giga. They still all follow the same rules you learned in intro and in DC. So binary engineering notations. This is where it starts to get really big. So in kilo, you have 2 to the 10th. Its original number is 1024. So you get 1024. So then you have mega, giga, tera, peta, exa, zeta, and yoba. And each one, you're just looking at these exponents and trying to calculate it out. If that makes any sense. Okay. So 2 electrical conductors. This is, excuse me. So serial representation. So we're dealing with things in series, yes? Okay. So series is slower than parallel. So it's 1 bit for each clock period. Telephone lines and intercomputer systems use these, but they're kind of disappearing slowly because we found out that parallel runs a lot faster and a little bit more easily. Nevertheless, this is a very good example of this. Okay, so standards are always everywhere in any field, right? It's not something you can get away with or away from. There are always regulations and such like that. Okay. So these are all some different standards that are used. So you have Ethernet cable, you have DSL, which is dial-up. USBs run with these. Because if you've ever, I don't know if you've ever really looked closely at a USB drive, but it's only got 4 strands of wire in there. 2 of those are power. One is to upload information and one is to download information, which is why they call it a serial. So USBs can run somewhere between 5 megabits per second, all the way up to gigabytes per second. And that's just how it uploads and downloads. So it's not extremely fast, it's not slow either. Got a question? So this is a serial signal. So you have your common pieces, you have your clock that's sending the signal back and forth, and you have your data that's coming in and out with that clock. Then you have what's called asynchronous signal, because if you look at these signals, they're just about the same right here on the clock. The data not so much, but the clock is exactly the same. For asynchronous signals, you'll notice that you have a big one, little, little, big, little. That means that the signal's not steady when it's moving from the transmitter to the receiver in this case. Okay. So differential signals. Okay. So where one goes high, the other one's going low. So these are supposed to mirror each other. Allowing for both upload and download. So we have what's called parallel representation. So in parallel circuits, what happens?
There's multiple paths.
Multiple paths. What else?
If one thing goes out, you can replace it and not worry about the rest.
There's that. What else? What's the biggest thing that we like about parallel over series? Or one of the big things?
Cheaper to replace.
Well, there is that. But the fact of the matter is, parallel is a lot faster. Okay? I'll say that again. Parallel is a lot faster than, say, a series circuit. Because it doesn't have to go through as many resistors to get back to where it needs to be.
And if it breaks.
What?
If something breaks, the whole thing doesn't go down, just that section.
Yep, that's always a good thing right there. So these can be very expensive, but they are very fast. So think dial-up. I don't know how many of you remember the old telephone dial-up that took forever. So whenever you got on AOL, it took you 20 minutes to get on AOL. Anybody remember that?
Don't remind me. Especially if someone picked up the phone.
Yeah, that would kick you off the internet. And then you'd be stuck waiting until they got off the phone so that you can get back on. Well, nowadays we have parallel representations. So if you look in your house, you should see two different jacks. One would be for the internet, one is for your home phone. So that would be kind of like a pair of parallel circuits. So this is found inside computers, printer interfaces, and small computer systems interfaces. So if you're talking parallel with this stuff, again, you're just trying to allow for a higher speed to be achieved. But again, it can be very expensive to achieve it. What's one of the things, some of the materials you can use for something like this? How many of you have heard of fiber optics?
I have.
So that's exactly in parallel, because with fiber optics, all it's doing is shooting that beam of light down several different rods at the same time and is able to pinpoint one versus another to help shift things. So here you got parallel, and you got your return line, you got your transmitter, and you've got your receiver. The transmitter is telling it different ones and zeros. The receiver is able to interpret it, and then the signal can return. Does that make sense?
Yes, ma'am.
Okay. So methods of communication. You have simplex. This is in one direction from the transmitter to the receiver. So how many of y'all remember talking about light sensors? Something like a light curtain. Okay, so what do? What is the purpose of a light curtain? Anybody just want to take a stab at it?
You talking about like the use of it or how it works? Normally, it's used to like stop people from entering a certain area and shut everything off, right?
Yes, but how does it work? Is the fact that it just sends that beam of light.
And then it reflects it back, and if it doesn't get it back, it shuts off.
Exactly.
But isn't there like two different types of light curtains?
And there's a lot of different types of light curtains, but the whole purpose of them is to make sure somebody not authorized gets into something where they shouldn't be. That's the whole point of that. So communication in one direction, so that's things like broadcast TV, radio, computer addresses, things like that. In other words, it's just meant to be sent, not received. I'm sorry, it's meant to be sent and received, but not sent back. That's what I actually meant. Yep. So this is a signal that goes in one direction, just like some light curtains. It just wants to hit the receiver on the other end so they can sit there and say, I did my job. Okay. So you have what's called half duplex, which is communication in two directions, but at different times. So CB radios, USB drives, and some versions of Ethernet are what these use. So it allows communication in two directions, but just not at the same time. In other words, take a USB for example. When you use a USB, are you able to upload and download on that thing at the same time?
Yes.
Only if you really have to work at it, because generally it doesn't like doing it. That's been my
It
experience.
takes longer when you're trying to do both.
Exactly. So, yes, you technically can do it. It's not generally advised you do so. Simply because you can overload something and break it. Okay. So then you have communications in two directions at the same time. So that's telephones and cell phones. Let me ask y'all this. What would a pager have fallen into?
Wouldn't it just be a receiver?
A simplex.
It would be half duplex, I think. If well, actually, it would be simplex because you can't send a signal back from your pager. You can only get a signal to your pager. So yes, it is simplex. What about your computer?
Half
Full?
duplex.
It would be a full duplex. How do I know that? Because I can send and receive information on this thing all day, every day at the same time, and it will not affect anything. Okay?
Wait, you said that one a computer would be half?
No, it's a full.
Oh, okay. So
A computer is a full duplex, and that's simply because it's able to send and receive information at the same time.
I just
So,
misheard you.
that's fine. All right, so we have 8-bit and 16-bit parallels. You have LPT1 and SCSI. And then LPT1 runs at 115 kilobytes per second. The other one runs at 160. Okay. So switches in electronic circuits are there to make and break circuit connections. Okay? They make and break circuit connections. Does that make sense to everybody? Okay. So manual switch or electromechanical relays are something that is typically very vital in automation. Why? Why would it be a big thing in automation?
I got it on the tip of my tongue. I can't remember if it's voltage or amps, but it can handle higher loads.
Okay. What's another good thing about it? Or what? Let me ask you this a little bit differently. What would you use it for?
E-stops?
E-stops are a great
Or
way to use these. What else?
like the main shut off.
All right. That's really nice and correct. Okay. So we have things like semiconductor devices, that's diodes and transistors, manual switches. And the interesting thing about them is the fact that they can change between open and closed just by flipping that switch. Okay. So the relay is a switch because it's an electromechanical relay. So everybody knows what a relay is, right? I'm not talking the one where people have to run at each other and slide a baton between each other and say, here, take this, run, run, run. In this case, we're talking about a electromechanical device that can be used remotely. How about that? So if I'm on one side of a piece of machinery and I need to start it and that starts on the other side, I can set up a switch. I can set up a switch so that I can trigger it remotely. Does that make sense?
Yes, ma'am. Kind of like when a room has 2 light switches and they both turn on the same lights.
Yes. They might be mechanically connected to those light switches and have just branched off, but they also could very well be using relays. You see relays a lot in industrial construction, simply because most of the time you don't want to get in with whatever's having to do the work. It can be quite dangerous, right? All right. So we have what are called normally open and normally closed. What is the difference between normally open and normally closed, guys? What is the difference between normally open and normally closed, guys?
Would it be that the normally closed always stays off?
Normally closed stays off until something makes it change states.
So essentially, it's their starting positions till they're flipped.
Yes.
Or till they're energized.
Yes, that's exactly what it is.
Don't we use this in robotics as well?
Yes, we do.
We use it in PLCs a lot too.
Yeah, I knew I recognized it from somewhere.
Well, normally open means that the circuit will not close until told to do otherwise. Normally closed means that the circuit will stay running until told to do otherwise. Does that make sense?
Doesn't it also mean if they're de-energized, they'll go back to those resting states?
Yes. To make it kind of funny for you guys, basically, these guys don't change states unless they're forced to. So think of them kind of like a door. If a door is supposed to stay closed 24/7 until somebody walks into it, that would be a normally closed door, right?
Yes, ma'am.
However, if you do have the open door and people can walk through freely, it won't stop them from walking in until the door is what?
Closed.
Yep, door won't close until it closes. So kind of like Newton's law of Newton's law, right? An object in motion stays in motion, an object at rest stays at rest unless acted upon by outside forces. Well, it's very true in this case as well, because unless an outside force forces this to change state, it'll remain either normally open, which again, that turns off whatever you've got going, or it's a normally closed, or it's a normally closed, which means it runs until you turn it off. Now that's a good thing for production, because why? Because you don't have to have somebody standing over it and going and constantly telling it to run or to stop or to shut down, what have you.
And it saves power.
And it saves power. Also saves time because the employee doesn't have to walk all the way around the machine just to turn it on. It's got a relay switch that allows them to do it remotely, right? Which frees up their time to do something else besides stand around waiting for the machine to do what it needs to do, because they've got to monitor it. Instead, we try to set up a lot of factories these days to where human interface is minimal, simply because it makes it easier to automate than what it used to be. Okay. So this is a switch. Relay switch. So what you can kind of sort of see, especially with these right here, this is a reed switch. So what a reed switch does is when it's turned on, it magnetically pulls the mercury to where the contacts are and lets it form up around those so that it can turn itself on and off. And yes, there actually is actual mercury in those. That's why they try and make it to where people can't get into it anymore. Too many people got sick from mercury poisoning. Okay. So the disadvantages of relays being used, you have to use current to operate it. It's slower by milliseconds. You have to have an energized relay coil. You have to work with timing diagrams and find some way to make it work in a way that won't interfere with what you're trying to do. Okay. So when the coil energizes, that means that the signal will go high. When the coil de-energizes, the contacts will open. So at 0, this one's giving an output of 5 volts. When this one goes to 5 volts, this one goes to 0 volts, and so on and so forth down the whole thing. This is how the clock would work. All right, so diodes. Who knows anything about diodes? What is a diode supposed to do? What is the diode? What is the purpose of a diode and how does it work?
Isn't it only supposed to go in one direction?
It's a one direction run, right? Because if it starts trying to come back the other direction, what does it do?
Blocks it off.
It essentially tells the electricity it shall not pass because he doesn't want it to pass. It's only supposed to be a singular direction that it runs. Okay. So current flow in one direction only. you have two different biases on these. You have the forward and the reverse. The forward, you have to put your anode at a more positive than your cathode, which we'll talk a little bit deeper about those when we get to lab. Have any of y'all ever actually played with diodes before?
Yes.
Yes.
I'm assuming most of y'all took AC already, huh?
Yep.
Okay. So with a forward bias, your anode is more positive than your cathode, so you get current flow. Whenever you reverse that, your anode becomes negative and your cathode becomes positive, so it stops current flow. So it's a one-way street. You can only go down it one way. It blocks itself off the other. Okay. All right, guys, let's take a short break. We'll come back. All right, so when you're using a diode as a switch, this is along the lines of I don't know how many of y'all have ever seen a water clock, but water clocks have check valves in them, and this acts exactly the same way. If any of you have ever taken hydraulics, pneumatics, a check valve is what keeps the water from flowing backward, water or air from going backwards in your system. It stops it right there and then to keep it from breaking your system. Okay. It's not perfect because you have to have approximately 7/10 of a volt across terminals when when you have it in forward bias. And in the reverse, it acts as an open. So in some ways that would be a good thing, in other ways maybe not so much. Since I know some machines that if you do that, it will just clear the memory of everything it ever knew. So you gotta be real careful on how you do this and how you make sure it works, because otherwise you can lose anything and everything you've done for the last month or two just by putting in a diode the wrong way. So always make sure you know what you're doing. Okay. So in the reverse bias, your current is decreasing, and in the forward bias, your voltage is increasing and your current is decreasing. Now on the reverse bias, it's a very gentle slope. On the forward bias, it's very steep. So what is AND logic? What is AND logic, guys? Or better yet, what are all the different ways logic is used? What are the different logics?
Is used in clocks.
Okay, so what are the logics? You have AND logic, obviously. What other logics are there?
Or, nor.
Okay.
NAND.
Okay.
Nor. Exclusive or exclusive. Nor?
Just to
Or
go
is that
back
only for
to,
PLC?
I think you're doing a little bit of repetition here. So what you should have had is AND or not, NAND nor, and then the fifth one is memory. I'm sorry, the sixth one is memory.
Okay, so the exclusives are only in PLCs.
I believe so, yes. You can create the exclusives with this stuff, but the basic logics that are something you use constantly are the basic 6. So and, NAND, or, NOR, NOT, and then you have memory, which is the CLIN circuit that keeps the circuit running until you tell it to stop, right? We'll talk a lot more about logic as we go through all this. So, which of these is AND logic?
The one on the left.
The one on the left? Okay. So, how is it AND logic? To me, yes, the one on the left is AND logic, because in order for it to get from point A to point B, it's got to push past, but not just one, not just a diode, but through the resistor as well. Okay?
So the one on the left is AND because the diode is facing towards the resistor, not away from it, right?
Yes. Because remember, I wish I could draw on this, but it only lets me have a laser pointer. With a diode, which side is the cathode side whenever you're looking at this diagram?
The line.
One with the line, right? The anode side is this guy right here. So when electricity tries to flow back into this, it works just like a check valve in hydraulics, pneumatics. And that is the fact that it will seal itself up so that it does not get backflow any further than it has to. Okay. So then if it's to become an AND circuit, your flow has to come from this direction, push through this guy, and then since I'm trying to get up this way, it's got to come through this and come up through this guy. Okay. And you could also, well, hold on. I might be going a little backwards here. No, that's right. Okay. So power comes through this guy right here trying to get out. So it is pushing back against the diode. So I'm having to double check myself here. So I don't want to tell you something wrong and be wrong. So OR logic would mean that one or another thing could lead to it moving, right? And AND logic, two things or more have to become utilized to allow flow. Would y'all agree with that?
Yes, ma'am.
Okay. So OR logic, you can literally say this or this will allow flow. With AND logic, it's this and this have to be in sync. So AND logic, I don't know how many of you watch old movies where in order to set off the nuclear explosive or whatever, they had to both synchronize how they turned those keys, and they had to do it at the same time. You know what I'm talking about? Somebody just gave the order to launch a missile, and both people have to put a key in the thing and turn it at the same time exactly. You know?
Yes, ma'am.
Okay.
Yes, ma'am. I follow.
So that's and logic. Or logic would say either person could put that key in and let that out. So all right. So we can also use transistors as switches depending on the application you're putting it in. You have what are called bipolar transistors. They have input signals at one terminal, and the other two become either short or open accordingly. There's two different types of transistors we typically use. Those are the NPN and the PNP. We'll go a little bit more in depth on those when we get to those. Okay. So again, for any of these, any diagram, follow the arrow, and it's supposed to show you how to set it up so it works well. So for this PNP, it comes in through E, has to hit at point B, and then comes out at C. And this P channel comes from D. It might even come from S2. They really didn't do a good job on that particular drawing. So you have what's called a collector, a base, and an emitter with transistors, right? So you have your base, which is this guy right here. This is supposed to be your collector. I might be saying that wrong. And this one would be your emitter, yeah. So this is your emitter, this is your collector, this is your base. So the base is where voltage comes in, your emitter pulls the voltage from the base out, and your collector is generally hooked up to something else to pull voltage from a different direction. So all three legs have to be in use on these. Then the NPN, you have your base that is feeding out to your emitter. Your collector and your base are both feeding into that emitter. Okay. So for an NPN, you have positive voltages from base to emitter with your collector to emitter junction shorting out. If it's in the on state. Negative voltage or zero voltage from base to emitter, and the collector to emitter is open, it's off. So these work both as on and off switches. Okay. Versus a PNP, which feeds negative voltages from the base to the emitter to put it on, and positive voltages or 0 volts to turn it off. So one deals with negative voltages happily, and the other one deals with positive voltages. Okay. Just as a quick question, how many of you have your books yet? Or
I will not get mine till right around this weekend.
okay. Guys, it would probably do you really well to go ahead and make sure you have those, or at least have them coming on the way. Because the books can carry a lot more information about this as well than what all I can cover in class, so please make sure you get your books. So then we have what are called integrated circuits. So IC circuits are kind of interesting. They can use transistor to transistor logic. They can do inversion, which is taking a digital input and complements it to the output. It allows for transistor saturation or cutoff. They also have what's called a totem pole output, which we'll talk about here in just a minute. All right, so if you've ever seen a computer chip, those little flat black chips, excuse me, this is where those come in. Okay, this is where these get used, as well as how to use them. So you have what's called a 7404. These are hex inverters. Okay. So they do 6 complete logic. So they have 6 complete logic circuits. As a matter of fact, these work as diodes. If you had your book, the really cool thing, or at least in my old book, is the fact that if you look inside the front cover, it has all the IC chips and how they're wired up inside. Kind of makes it cool. But these particular ones are set up as diodes. In other words, they allow flow in one direction. It has 14 pins and 7 on each side. Pin 7 and pin 14 are your voltage and your ground, respectively. The other pins give you 6 different circuits to play with. All right. So we'll probably be playing with those as soon as we get to lab on, I think y'all are allowed on campus as of the 25th. So that's not this coming week, but the week after. So we'll get through some more lecture before we go to first labs, which I wish I could say different, but that's COVID policy right now. The dual inline package is, you have a normally closed. It's not physically or electronically connected. Instead, it's electrically connected in here. Sorry, not electrically connected. It's built-in circuits. Let me put it that way. Okay. So, looking at this, so those are diodes, right? It's not a perfect diode, but basically what this is telling you is that it seals off at one end and it allows flow in the other. So again, your 14 and your 7 are your what? What are 14 and 7, guys?
Is there a relay?
Nope, 14 right here is your voltage in, 7 is your ground. So this guy can't be electrically active on his own. He's actually got to be hooked up to be able to run the chip.
Is this one of those chips that go inside like a digital clock to change the numbers?
We will be talking about those, but not this. Not this particular one. This one you might find in something like a TV or a radio. Theoretically, you could find it inside a digital clock. It would be depending upon how the person that engineered that particular clock decided that what parts they needed to get whatever effect they were looking to get. I mean, that's just how that kind of works out. Is it's the engineer that has to determine, oh, I decided that this works best for this. It works to make sure that da 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 da. This right here would just kind of stabilize the signal to keep it from causing too much havoc. Like I said, they work kind of like a diode. It's a flow in one direction only. Does that make sense?
Yes, ma'am.
Yes, ma'am.
Okay. I hate to think I'm trying to talk gibberish to y'all, so that's kind of why I keep asking. Okay. All right. So you have what's called the CMOS integrated circuit. This is long way saying complementary metal oxide semiconductor. Again, these are integrated circuits, so those are the little chip things that we play with. These use very low power consumption. Most of these chips use very low power consumption. This can be used in battery-powered devices. It gives a slower switching speed than the TTLs or the I cannot remember what TTL stands for right now. Oh, it's a transistor to transistor logic, excuse me. Yeah, for some reason that was not coming into my head. So it's a bit slower in switching speed than a transistor to transistor logic, and it's very sensitive to electrostatic charges. That's why whenever you're working on things with integrated circuits or anything like that, what do you need to make sure you do before you really start working with it?
Make sure the power's off.
Well, you need to make sure your power's off, but you also need to make sure that you do not carry any static electricity. Because believe you me, static electricity can and does kill any and all electronics if you are not careful about how much you carry on you. You have to remember, guys, whenever you're dealing with IC chips and stuff, is that these are very delicately balanced so that they work correctly and most efficiently. But at the same time, if you have any transient voltages sticking to you, which this kind of time of year we generally have a lot of that kind of stuff, right?
So how do you counteract when you're working with that?
Well, generally you have what are called static combs or static bands. They make Velcro bands that go around your wrist and then are connected to something metal to help pull charges like that off so that it doesn't randomly come off you and hit the circuit.
Okay, so it's the same. Like I didn't know if it had to deal different than like regular computer parts, but so essentially it's the same thing. You just clip to something metal.
Yes.
While you're wearing that band.
Yes, because if you don't connect to something metal or something that'll help pull charges off, you can build up enough of a charge that it'll pop from you to it and it'll fry out your whole circuit. That's how delicate some of these can be. So anytime you work on anything electronic, technically what you're supposed to do is make sure that you're free of any and all static. Here in the winter time, that's a little harder than during other times of year, right?
Yes, ma'am.
Because other times of year we have enough moisture in the air to help absorb that static electricity and dissipate it. But here during winter, not so much. Which is why when you get in and out of your car during the winter season, what do you typically have going on around you? Pretty much man-made. You get man-made lightning, right? If you got a fleece jacket and you get in and out of a car that's got fabric seats, you can hear it crackle on you. Or if you've ever put stuff in the dryer without a dryer sheet and it becomes statically glued together, so when you rip it apart, you can actually hear the little bits of. It's not. That's the kind of stuff we want to avoid.
If you're in a completely dark room, you can see it.
Yep. Kind of like if you shuffle your feet across a carpet, walk up to something metal and touch it, or walk up to another person and touch them. You can feel that popper. And you can generally hear it too. Sounds something like zneep, ping. That's what you're trying to avoid having come in contact with your computer. Simply because that is not good for it. Okay. You got any questions for me so far? All right, we'll keep moving. So surface mounted devices. Okay, so this goes back again. We're in integrated circuits here, guys. So surface mounts are very common with these. Just kind of a quick raise of hands. How many of you have ever decided something's broken, so thus I'm going to be the one to try and fix it? So you tear it open, and you get to see all the little black chips and stuff all over it.
I fixed my Xbox controller.
Oh, that's cool. But that was really interesting to tear into.
It was actually pretty simple. I had to replace one of the buttons.
Mm-hmm.
Because I dropped it and it broke.
Well, my best one I can tell you is our microwave started emitting the black, noxious smell of electrical nastiness that comes whenever something starts to try and burn out. So my dad and I took our microwave, brought it down, took it apart, and I figured out that it was the diode. It's the thing that charges and discharges. It's a. It'll come to me here in a minute. The thing that charges and discharges high voltage. I can't remember what it's called right now. It'll come to me here in about a few minutes, and I'll sit there and go, "Oh right, it was that."
Is it a capacitor?
Yes, a capacitor. Thank you. For some reason, my brain decided it didn't want to have that one. Okay, so yes, so I ended up plugging it up, running it real quick, and figured out the capacitor had gone bad in a very bad way. So we ended up having to replace the capacitor, which was a lot cheaper than having to replace the freaking microwave. If you've ever had to replace a microwave, it's not cheap. And that's really something that you will get what you pay for on it. Okay? Don't ever let anybody tell you different. You get what you pay for with electronics sometimes. If you buy something really cheap, it's not going to last long. But anyway, so yes, if you start breaking into stuff like that, you can find that you can fix it yourself sometimes. But when you do, you also get to see all the very interesting bits and pieces that are on the inside, like integrated surface mount chips. If you ever open up one of the more modern televisions, like a flat screen that's gone bad, you'll see it then too. It's really, really cool to open those up and see, oh, this is how they built it. Believe you me, I find it very fascinating to open that kind of stuff up. That's why I got into this. So surface mount devices, they reduce size and weight. Why do we want to reduce size and weight? Why would that be really important to us?
The cost of it, for the materials to make it.
The cost of it, the materials that make it. What about just taking up less space? How many of you remember the really big, bulky televisions they used to have all the time? Heck, it was only 20 years ago, so hopefully all of y'all remember whenever we had the big, bulky TVs that were heavy as all get out, that you had to have 5 people to lift it someplace. But they were the big screen TVs of their day, and they're also the kind of TV you can't throw away or give away anymore. But y'all know what I'm talking about, right?
Yes, ma'am.
So, or even just look at your cell phone. If cell phones were built with the kind of circuits that we had back in the day, how big would they be? Would you be able to fit it in your pocket or your or anything like that, or would it have to go in something much bigger? I think we all kind of understand. You have to have something a lot bigger, right? Because it would fit. We have smartwatches now that can function as phones. We have come so far in technology just by having these integrated circuits that we use. So it saves on weight, it saves on space. It lowers the cost of manufacturing the circuit boards. And you solder them directly to the footprint. We'll talk about a little bit about soldering when we get to that point, by the way, guys. How many of y'all actually got to mess around with soldering and desoldering things?
Uh,
It's kind of fun. Soldering can be a lot of fun if you make sure you do it right and don't burn yourself.
yeah, there's definitely an art to it.
Well, there is. It's can be very satisfying if you put the right size bead down and it sticks and it's all good. It is extremely satisfying. So just to kind of keep that in mind. So the chip density can be increased because they're smaller. We can put more per square places than if we simply used bigger chips, which means we can allow it to do more. So that's why the newer watches can do things like do EKGs, which anybody know what that is? It's what are called echocardiograms. It's something used for when you have had strokes or heart attacks. They have to monitor your heart. Well, now you have watches that can do that instead of having to have specialized devices to do it for you. These things can throw that out there. You can go with higher frequencies. Basically, these have changed how we live and work in our world, right? We now have computers and tablets that if you went back 20 years or 30 years with the same technology we have today, what would they think? It'd be a miracle, right?
I think you're an alien.
I don't know so much about alien, but it would definitely be very different for them because we could not conceive of it at that point. To us, it was this concept of, oh, now we have cell phones that are less than an inch thick most of the time. Or we have cell phones that are able to have high def screens and they can do all these video games. They don't just call people anymore. We can actually do a lot with them. You can carry a whole computer in your hand.
Yeah, like what, the 1980 something computing power? We have more computing power in the palm of our hand than we did back then.
Oh yeah. Think about the memory devices we used to use. We used to use freaking floppy disks, for crying out loud. How many of y'all remember those suckers?
What about the rolls before that?
Yeah. I mean, that's just how it's gone for years, guys. So with these integrated circuits, we have pretty much changed the landscape of the world just by having something that is able to be small and is able to be used in smaller spaces. Right? Just figured I'd make the point. So these are surface mounts. You can literally, doesn't show really great pictures of it, but these are soldered onto the boards right here with these little legs. Again, I'll show you kind of soldering and desoldering once we get into the classroom. It's really a lot of very interesting fun. Okay. So you have some that are small outline with very low complexity logic. And then you have plastic leaded chip carriers with more complex logic. Again, a lot of this tends to depend on engineers, which you might have to become the engineer to basically create these circuits. So it pays to know what computer chips do which. All right? Because one day your boss might come up to you and say, oh, we need you to design this kind of a circuit so that we can make this more efficient and make the controller smaller. Yeah. That kind of stuff does happen every now and then. So this is just a, so if we look at this guy right here, this is the dual inline package. In other words, he just has legs going down the two sides of him. Like this guy right here, he's just got the legs that go down two sides. Those are dual inline packages. Versus the plastic leaded chip carrier, which is this guy right here, which has legs on all four sides. I'll see those? I'll see that all right?
Yes, ma'am.
Okay. So the digital level for one is commonly a voltage of 5 volts. 0 volts is used for the 0 level. And we use oscilloscopes to help us observe this. So how many of you are familiar with the use of oscilloscopes? Okay. We'll be going back over how to use oscilloscopes whenever we get to lab. Simply because I think hands-on is a little bit easier to work with oscilloscopes than working hands-off. At least that's how I've always seen it. So the frequency of clock waveforms is equal to the reciprocal of the waveform's speed. We use transmission of binary data in the serial format using a single conductor with ground reference. Parallel is much faster than serial, by the way. Don't forget that. But then again, if you think back to when you were in intro and DC, parallel circuits, they're faster and more efficient than series circuits, right?
Is that?
Kind of like a 4-lane highway is a lot faster than a 2-lane highway, right? If you really want to kind of have an analogy for that. There's a reason parallel's faster. Okay. Electromechanical relays are capable of forming shorts and opens in circuits requiring high current values but not high speed. Simply because when you're dealing with speed, you gotta be really careful about making sure your signal is got the time to go through. But not just that, sometimes you have to wait for it to be able to be registered as it's gone through. Excuse me. So diodes are used in digital circuitry when there's a requirement for current to flow in one direction but not the other. Again, that can go back to working with hydraulics and pneumatics for those of you that have done that in my class. You have those check valves that only allow the flow one way, right? Same thing here, we allow the flow of current only in one direction. It might be just because you're trying to protect the circuitry that's downstream, right? Make sure to filter out anything that could possibly cause harm to your circuit later on. Because these aren't supposed to handle high voltage. They're supposed to all be low voltage circuits. Transistor is the basic building block of the modern digital circuit. It can be switched on or off by applying the voltage at its base connection. This is where you would have to have switches, and this would be able to be remote circuits. Transistor to transistor, logic, and CMOS integrated circuits are formed by integrating thousands of transistors in single packages. They're the most popular ICs used in digital circuitry for a reason that way. Okay. And then surface mount devices are gaining popularity over the through-hole style, which is the other style, because they're smaller size and reduced manufacturing cost, and the fact that everybody wants everything smaller these days, right? Forget big and bulky, we want small and tiny. Does that make sense to everybody?
Yes.
All right. Let's see. I'm going to pause out this recording.